everybody, Dr. Urban. I'm going to go over a bit more information on circular motion. The first 3 videos in this series dealt with circular motion in the X direction. So whether that was something perhaps being tethered on the end of a string and moving around in a flat horizontal way, or it was a car, say, entering a cul-de-sac and going around a flat curve, or a car or something entering and going around a banked curve or an angled curve. We're going to look at things a little bit differently. So we're not going to be in the X direction, so let's erase that. We're actually going to be talking about the 2 scenarios where we have circular motion in the Y direction, or the up and down direction. So let's go ahead and just draw essentially 3 scenarios. So we have a flat section of road, and then let's say we have a curved section of road here, and then later on a very like a dip in the road. Okay, I know this is exaggerated, but that's the point. So over here, if I were to have a car moving along, okay, I would know, and these are sort of going to be a hybrid between actually drawing like where the forces are and free body diagram. So we know in this case this object has mass, it's going to have a weight vector here downward, and then there's going to be a normal force back upwards if that car is over here on the flat and level ground. And we know those are going to be equal and opposite one another in the Y direction. But what happens when the car goes over a hill? So this is you on top of a hill. And you know what this feels like. You feel not necessarily weightless, but you feel like you weigh less, okay, at the top of a hill. So if you're getting, don't do this, but if you were going quickly over something that is a hill like this, you're going to feel weightless. Sometimes you feel like this if you're in an airplane and the airplane begins to nose over, you're in circular motion and you feel a little bit weightless. And then if you were to drive on and go into this dip over here, and you're going, and the dip's big enough, and you're going at a decent speed, you're going to feel sort of pressed down into your seat. So here you're going to feel like you weigh more. And whenever we talk about our weight not actually being our weight, what we're referring to is something with normal force, okay? So we're going to need to find the normal force. The other way we title this, it is the normal force, but you might see it in the text called weight apparent. Okay, apparent weight. So what if you were sitting on a scale in this car here, your weight would read your weight over here in this flat area. If you move through this curve, you will actually, the scale will read less. Here in this dip or depression in the road, you will look like you weigh more. The scale will read more than your weight. So how do we deal with these? Okay, so the first thing I need to do is I need to show where I am, and then I need to show here that this is a radius. This is the radius of the circle from here to here, okay? Make note that it's in the Y direction. And if you were in the car, you would have to look downward with your eyes. So we know if we're in circular motion that that I'm going to draw these beside each other. Obviously, they're directly down from the car, but just so you can see it, centripetal acceleration and A sub C and centripetal force are also, because centripetal acceleration is in that direction, that is caused by centripetal force being in that direction downward. That is going to be a negative net force. The converse is true over here. In the bottom of this dip, you'd have to look upwards to see where the radius of that circle is. Okay, or the radius of the curve in the road is right through here. And so we know that centripetal acceleration, and again, I'm drawing them side by side just so you can see them, centripetal force must be in the direction of the radius, and so these are going to be positive. So if you keep that in mind, we're going to draw the 3 free body diagrams for these scenarios, and this will make a lot more sense. And so I need you to be able to do this, okay? We've already done this first one. So we know here's my object, so I have the weight vector downward, and I have the normal force upward in the Y direction, okay? And that when I sum forces in the Y, equals mass times acceleration in the Y, but it's not accelerating in the Y direction. There's actually, in this scenario, there's no Y motion, so therefore there's no Y acceleration. So this goes to 0, okay? So what I end up with is I have my normal force upward minus weight equals 0, or my normal force equals my weight. And we've done this a bunch of times throughout chapter 5. Now, if I look at this separate, break these into 3 separate thoughts. So let's actually draw the free body diagram for going over a hill. Okay, mark your XY axes. Here's your car. Okay, I do have weight downward, and I would think that I would have just that same normal vector up like this, but hold on. I'm going through a curve, so I have a net centripetal force in the negative direction. So that is going to be subtracted from my normal force. So actually my normal force is going to be less. My normal force is less. That would mean that makes sense. If my normal force is less, that's my apparent weight, so I would weigh less. So let's figure out how to write this out. So when I sum forces in the y equals mass times acceleration in the y, in this direction, I do have centripetal acceleration, or I have acceleration, okay, in the y, and it is centripetal acceleration. Remember that centripetal acceleration equals v squared over r. So actually the sum of the forces equals mv squared over r. Okay, so let's list my forces. I have normal up minus weight down equals mv squared over r. But the sum of my forces, this whole term, I drew it. My radius is below me if I'm at the top of the hill. The centripetal force has to be directed to the center of the radius. So that's downward or negative from my position. So my centripetal force is negative. This whole term becomes negative. So it's actually normal minus weight equals negative mv squared over r. So when I solve it for normal force, that is weight minus mv squared over r. And I could go ahead and take it one step further and say weight apparent equals weight minus mv squared over r. So basically what I'm saying when I'm on top of a hill, I should weigh less. So let's make sure this is correct. It's my weight minus my mass, the velocity at which I'm moving. The velocity isn't changing. I have acceleration because I'm moving through a curve over the radius. This whole term is negative, so my weight minus the effect of my mass moving through the curve. So basically, it's my weight minus the effect of my mass moving through that curve. Let me scoot this up just a bit. Of my mass moving in circular motion. Okay, that's centripetal force. That's what I'm subtracting here. So yes, my weight is less, my weight minus the effect of the hill. So if you remember from lecture, if you've ever seen this done, you know that the answer over here is going to be your weight plus the effect of your mass moving at whatever velocity through this. But let's just go ahead and go through the process. So you can do these free body diagrams. So here is the car, or your mass plus the car, weight equals mg. And like I said, if we were just sitting out here on the road, on the flat surface, normal would be equal and opposite. But in this particular case, if you see, I am at the bottom of a curve. Here is the radius of that curve right here. It's a distance up. It's up above me. Anytime you're in circular motion, the force is directed to the center of the curve, or the center of the circle, in this case up the radius. So I actually have a net, my centripetal force is my net force upward, so actually my normal force is actually going to be much greater. So when I sum forces in the y equals mass times acceleration in the y. Now the car is moving at at one velocity. Your car isn't speeding up or slowing down, but it has acceleration. It has centripetal acceleration because you're moving through a circle. Okay, so that's centripetal acceleration is v squared over r. We already did this just 1 second ago, v squared over r. And so when I sum those forces, I have normal up minus weight equals mv squared over r. And I know that that net force stays positive, so I don't need to actually write a sign there. And so I put my vector symbols in there. Normal equals weight plus mv squared over r. So my apparent weight equals, my weight plus mv squared over r. Okay? Does this make sense? Do I feel heavier at the bottom of the hill? Yes, I feel pressed into my seat. Pressed into my seat, I feel like I weigh more. That is going to be normal force. And when you say weigh more, we know that's normal force, or some textbooks say apparent weight. That is what I'm going to be looking for. That is what I found. It is my weight plus the effect of my mass moving at this velocity through this particular radius.